So today the discussion is going to be about the electrostatic potential, and it's a huge subject. We're actually going to spend a lot of time on this, and as usual, this is the kind of thing which you have also for a good deal seen already. I've actually pre-written some of the notes for today just because it's like basic recall of things that you've already seen. But let's just walk through this discussion, making sure that you're happy with everything that's in there. Question? Yes. I thought they were already. Pick my assistants. Okay, let me check at the break or just after, because this was meant to be. Yeah, the kind of discipline I wanted to have is that the solutions were put either at the end of the day of that particular exercise session or the day after at most, quickly after. So if that's not the case, then just.
Yeah, I just wondered if I think for the first one they were published and the second one I don't know they are.
Of course, with this understanding, right? So this observation, if we give you a numbered exercise in Purcell-Morin, then the solution is in Purcell-Morin, and then we're not posting that solution because, we're not going to do better than Purcell. Right? So, okay. So let's see how we do. Maybe get rid of this. So the electrostatic potential, again, this is content that you've seen in your first course on electricity and magnetism, and it connects to the discussion that we were having previously about work. So we started the course talking about force. Force integrated over a displacement distance gives you work, the energy difference between beginning and ending configuration. So just a little rehash of these things. What did we have? We had earlier that this work was just a line integral from your chosen point A and up to a chosen point B of the force along the displacement. And then this force was, of course, given to us by the Coulomb law. Then we introduced the abstraction of the electrostatic field, saying that the force itself is proportional to the charge of the particle that you're using to measure the force. Therefore, there's something higher, the electrostatic field, which just gives you a kind of source vector field from which you can compute any force if you know the charge of the particle on which the force you want to calculate. So that was one thing. And then by the kind of fact that there's no perpetuum mobile here, these forces are all conservative, an integral over a closed loop of the electrical field vanishes, okay? Because you do a cycle, you come back to the same place, nothing's lost, nothing's gained, you come back to the same place at the same energy. And this was, you remember, quite important because it showed us through Stokes' theorem that the curl of an electrostatic field was 0, and we wrote that in red, that it was for electrostatic fields, because we'll have to revise that later on. Okay, so now just one other abstraction that we're doing here is that we're saying, well, actually, because I've got the fact that these line integrals over closed circuits are 0, it means really if I choose a certain reference point and I decide to compute a scalar number from the line integral from this reference point to whatever point I'm interested in of this electric field, I will get a kind of consistent construction. Namely, if you give me an origin, a reference point, and you give me an evaluation point, then I will be able to compute this value according to my choice of the path linking the origin to that point. Right? I can just do an integral which goes straight up to the point like that, or I can decide to go putz around the other way, come back, and then go to the same point. Provided the endpoint is the same, I will obtain the very same value for this number. And this number is a scalar because we are integrating along a line and we're doing the dot scalar product between the field and the displacement along this line. This is the definition of the potential. I really hope that you recall that in detail from your first course in electricity and magnetism. Okay, so just the potential and why it's kind of uniquely defined up to a constant. So that's the idea. The potential itself does refer to a particular reference point that we have to agree upon, we can put it at infinity typically. That's the simplest case. It doesn't have to be the case. Provided we agree, then all the values of that thing are well defined. The thing that is automatically well defined, of course, is the potential difference between any 2 points, because in the expression for the potential difference, the position of the original reference point disappears. Okay, so that's like everybody agrees on what this potential difference is. Okay, so this is the equation. Potential difference is just minus the line integral of the field between the 2 points. Okay, so if anybody has any discomfort with any of this, speak now, or come again later. Yeah? Okay, this is all cool, yeah? Right. Now, the potential is again something that you will have calculated for a number of very, very simple circumstances. The very first simple circumstance that we can consider is a charge Q situated at the origin. We put it at r is equal to 0 for convenience. And now we want to ask, what is the potential in space that originates from that charge at the origin? So what do? We start at infinity, very far away, Canada, where I come from. And then we integrate all the way up to here, the value of the electrical field along the displacement. In order to make our lives easy, we're going to do a line that is strictly radial. Okay, so there's no putzing around. Strictly radial from a certain starting radius, which we'll put at infinity, down to the radius of the evaluation point you're considering, where we use spherical coordinates centered on the origin, namely on the position of the charge. Okay, so that means that this line integral here gets translated into its explicit representation, having chosen our coordinate system here. For now, it's a scalar integral over the radius that I just write as r prime here. That goes from infinity down to r. And then the electrical field is just, we remember that, right? So q over 4 pi epsilon 0, 1 over r prime squared. Now I just integrate this, and I am left with just the 1 over r form. So wherever I am away from a certain charge, a value q, the potential that I will feel from that charge is q over 4 pi epsilon 0 times 1 over the distance between my evaluation point and the charge. Okay, so again, I assume everybody is very happy with this. I mean, you might not be happy with my handwriting, I see. There. Okay, yeah, sorry. So this is my equation labeling. This one, oh yeah, so at origin. So the charge Q is positioned at the origin at r is equal to 0. Here, Q over 4 pi epsilon 0 with 1 over r.
Right part of the screen is.
You're joking me. We'll do it this way. Is this better? Okay, thank you. Yes, I could do this. Does that help? Then we can give ourselves a little bit more space, right? Okay. Okay, so that's the potential from a single charge. Yeah, everybody happy with this? If nobody interrupts, then I assume everybody's happy. So, and then by the principle of superposition, we know that if we have a distribution of discrete charges all over the place, then the total field, the total force is the sum, the linear sum of, vector linear sum of the forces. Therefore, by abstraction, the field is the linear sum of the fields. And because the potential is just an integral of the fields, therefore, the potential is also the direct sum of all the potentials, right? So therefore, the potential coming from a collection of charges Qi, each situated at their own position Ri, is simply the algebraic sum of the Q over distance factors that you have there, multiplied by this wonderful thing, 1 over 4 pi epsilon 0, that pervades everything we do. Okay? So everybody's happy with this, right? And then we can introduce another abstraction, namely move away from the discrete distribution of charges and say, oh, we've got of the order, 10 to 23 charges moving around. It looks like I've got this fluid in space that contains charge. And then in each little volume, there's a certain charge density, coulombs per unit volume, per cubic meter. And that gives us the charge density rho. And if we know the charge density rho in space, we can compute the potential that it creates in other places by performing the expected integral of, again, by superposition, taking all the little chunks, rho d volume, summed up over all the places where rho doesn't vanish, multiply by 1 over the distance. Thank you very much. Multiplying by 1 over 4 pi epsilon 0. Question? So here, this is phi at r. So r is the evaluation point, the point at which I'm measuring the potential. The integral is over the sources. So other places r prime, and therefore I'm interested in the density of charge at position r prime. And this contributes then an amount of charge which is rho of r prime with the differential volume element, 1 over the r minus r prime. Is that cool? Seriously? So I've kind of cut the all the audio on this one, but let me do that again. Does that? Yeah, I mean, hopefully that helps. Just like killing the bird repeatedly, and then yeah, we'll see. One day it's going to be dead. Okay, so for volume charge distributions, it's just like that. For the case of surface charge distributions, maybe you've got like charge sheets. Then you would just integrate once again the charge in a certain place with 1 over the distance with the evaluation point. But now you would do a surface integral, and you would have a surface charge density, traditionally denoted sigma, integrated over. And if you had a line charge, then you would just do the integral along this line. If you had like an insulating cable carrying charge, you would just do an integral like this. It's always the same idea. Just charge divided by distance, and you sum over all the charges, and then you get your potential. Okay? Question? What I would mean by this thing here, if I can get my here. So what I mean, so d r prime. Oh, sorry. So what I mean with the d, give you a better color. Sorry, just. What I mean with the d r prime, it's the 3-dimensional object, if you want. So it's a notation. I could write a d3r or something if you preferred. But really, what this means would be, if you're using Cartesian, you would do dx, dy, dz. Or if you're using circle, you do r squared sine theta, dr, d theta, d phi, etc. It's the volume differential element. I could perhaps write it as d tau prime, which is what I've done in the past. Would you prefer that? What I mean here is that it's the 3-dimensional element. So maybe let me. If you understand what I mean with the tau prime like this, then we'll be happy. Yeah. So it's it's really the volume element in the chosen coordinate system that you work with in this. Right? Okay. Okay, so that kind of gets us started, just these expressions that